Hello viewers, I Nilofer Zargam welcomes you again to the second part of differentiation, applications of differentiation. In the last script we have discussed the concept of differentiation. Differentiation helps us to find out the average rate of change in the dependent variable with respect to the change in the independent variable. It makes differentiation to have applications. Rate of change of quantities is involved in various scientific formula and results. It is often that in business we want to know change in revenue obtained with respect to the change in the price, change in cost with respect to the change in output, change in demand with respect to a small change in income, etc. Differentiation also helps in finding out the maximum and the minimum values of the functions in many cases. So in this script we will study the rate of change of one variable with respect to another variable and maximum and minimum of functions. But we must first understand the following concepts before proceeding further. Let x and y be the two variables such that y is a function of x. Differential coefficient dy by dx represents the rate of change of y with respect to x. So in other words, the expression rate of change of function means the derivative of the function. We know that dy by dx of f dash x, that is equal to limit del x that is to 0, f of x plus del x minus f of x, the whole thing divided by del x, and f dash x1 equal to limit del x goes to 0, that is of f of x1 plus del x, that minus f of x1 divided by del x, provided that the limit exists. When x changes from x1 to x1 plus del x, f of x1 plus del x minus f of x1 is the increment of y or function of x, and del y by del x is equal to f of x1 plus del x minus f of x1, the whole thing divided by del x, is the average rate of change of y with respect to x when x changes from x1 to x1 plus del x. Hence dy by dx or f dash x at x equals to x1 is the instantaneous rate of change or simply rate of change of y, that is equal to f of x with respect to x at x equals to x1. Let's see first example over here. Find the average rate of change of the function f of x, which is equal to 3x squared plus 4 when x increases from 3 to 3.5. Find also the instantaneous rate of change of f of x at x equals to 3. Now let's see the solution to this example. At any point x equals to x1, the average rate of change of f of x will be equal to f of x plus 1 plus del x minus f of x1, the whole thing divided by del x. Here we see that f of x is equal to 3x squared plus 4 and x1 is equal to 3, and del of x1 will be 3.5 minus 3, that is equal to 0.5. Therefore f of 3 will be equal to 3 into 3 square plus 4, that is equal to 31. Now f of x1 plus del x is equal to f of 3 plus 0.5, that is equal to f of 3.5. So we find the function of 3.5, which is equal to 3 into 3.5 the whole square plus 4, and that is giving us 36.75 plus 4, that is finally giving us 40.75. Therefore average rate of change of f of x with respect to x at x equals to 3 is f of 3.5 minus f of 3, the whole thing divided by 0.5. So that is equal to 40.75 minus 31, the whole thing divided by 0.5, which is equal to 9.75 divided by 0.5, which is equal to 19.5. So that is per unit change in x. Now f dash x is equal to 3 into 2x, so that is equal to 6x. So at x equals to 3, f dash 3 will be equal to 6 into 3, that is equal to 18. So this shows that the instantaneous rate of change at x equal to 3 will be 18. Let us see the second example here. For the function y equals to 500 by x, find the average rate of change of y with respect to x when x increases from 30 to 30.5 units. Also find the instantaneous rate of change of y at x equals to 30. Now let's see to the solution. The average rate of change of y at any point when x equals to x1 will be equal to f of x1 plus del x minus f of x1, the whole thing divided by del x. Here y is equal to, we know that 500 by x, and x1 is equal to 30, and del x will be 0.5. Therefore f of 30 will be 500 by x, so that will be equal to 16.67. And f of x1 plus del x will be equal to f of 30 plus 0.5, which is equal to f of 30.5. So f of 30.5 will be equal to 500 divided by 30.5, which will give us 16.39. Therefore, average rate of change of f of x with respect to x at x equals to 30 is equal to f of 30.5 minus f of 30 divided by 0.5, which is equal to 16.39 minus 16.67 divided by 0.5, which is equal to minus 0.28 divided by 0.5. That gives us minus 0.56. The negative sign indicates here that y decreases per unit increases in x. Now if f dash x is equal to 500 into minus 1 divided by x square, that is at x equals to 30, f dash 30 will be minus 500 divided by 30 square, that is equal to minus 0.56. This shows that the instantaneous rate of change at x equals to 30 is minus 0.56 units per unit change in x. The negative sign here indicates a decreased rate of change with respect to x. Most of the time, more than one variable is involved in many practical problems, and they are all functions of time, t. In such situations, by using the given conditions, we first find the relation or relations between the variables and then differentiate both sides with respect to t to find the relation between their time rate of change. Using these relations, we finally achieve the following desired results. For example, let y equals to function of t and x equals to function of t. Then dy upon dt is equal to dy by dx into dx by dt, that is equal to f dash x into dy by dt. This gives the rate of change of y in terms of the rate of change of x. Let's see example number 3 here. A stone is dropped in a quiet lake and waves move in circles. If the radius of a circle increases at the rate of 6 centimeter per second, at what rate is the area of the circle increasing at the instant when the radius is 12 centimeter? Now let's see how we find the solution to this. Let r be the radius and a the area of the circle at time t. Therefore, we have dr by dt, that is equal to 6 centimeter per second, where r is 12 centimeter. Now for a circle, we know that area is equal to pi r square. Now differentiating both sides with respect to time, we get dA by dt, that is equal to 2 pi r into dr by dt, which is equal to 2 into 22 by 7 into 12 into 6, that gives us 453.57 centimeters square per second approximately. Now let's see the fourth example here. The side of a square sheet of metal is expanding at the rate of 4 centimeter per minute when heated. At what rate is the area of the sheet expanding when the side is 12 centimeter long? Now solution to this comes as, let x centimeter be the length of each side of the square at any time t. Then according to the given condition, dx by dt will be equal to 4 centimeter per minute. Now if the area of the square sheet at any time t is denoted by capital A, then capital A will be equal to x into x. So that is dA by dt will be equal to d of x square by dt. So that is equal to 2x into dx by dt. So that is equal to 2x into 4, that is equal to 8x. Now when x is 12 centimeter, dA by dt will be 8 into 12, which is equal to 96. Hence the rate at which the area of sheet is expanding when its side 12 centimeter is 96 centimeter square per minute. For a function y equals to f of x over an interval where x goes from a to b, if a smaller than x1, smaller than x2, which is smaller than b, is f of x2 is greater than f of x1, then function y equals to f of x is said to be the increasing over an interval a to b. Similarly, for a function y equals to f of x over an interval a to b, if x1 is greater than a and x2 is greater than x1 and b is greater than x2, then function of x2 will be smaller than the function of x1. Then function y, which is equal to f of x, is said to be decreasing function over an interval a to b. Now in the first graph we can see the function f is increasing, while in the second graph we can see the function f is decreasing. Let y equals to f of x be a function which is differentiable over an interval a to b, and let c be any point in this interval, that is c belongs to the interval ab. Then if f dash c is greater than 0, the function f of x is said to be increasing at c, and if f dash c is lesser than 0, then the function f of x is said to be decreasing at c. On the other hand, a function y equals to f of x is said to be stationary at a point if it is neither increasing nor decreasing at that point of the interval. The point at which f dash of x is equal to 0 are called critical points of f of x. We come to example number 5. Now show that the following functions over here given. The first function x cube minus 3x square plus 3x increases as x increases, and in the second case y equals to x minus 1 by x increases in r except at x equals to 0. Now let's see the solution to this. Let the function fx equals to x cube minus 3x square plus 3x. Then we see that f dash x will be 3x square minus 6x plus 3, which is equal to 3 into x minus 1 greater than 0 for all x except when x equals to 1, and f dash x will be equal to 0 at x equals to 1. Hence if f of x, which is equal to x cube minus 3x square plus 3x, it increases as x increases except at x equal to 1. Let's come to the second one, when we are taking f of x equals to y, which is equal to x minus 1 upon x. Now here we find f dash x, that is dy by dx, that is equal to 1 minus in the bracket minus 1 into x raised to the power of minus 2. So that is equal to 1 plus 1 by x square, which is positive for all the real values of x except at x equals to 0. Therefore, we say that f dash x is greater than 0 for all real values of x except at x equals to 0. Hence, the function y equals to x minus 1 by x is an increasing function of x at all the real values of x. Now, consider the graph for a function f of x. In the graph, consider a small interval a, b. In the interval a, b, f of x is increasing to the left of point M and decreasing to the right of the point M. Therefore, at x equals to x1, f of x attain its maximum value in the taken interval. The slope of the curve is positive. When the curve is increasing and is negative, then the curve is decreasing. Since dy upon dx gives the slope of a curve, dy upon dx, or we can say f dash x, is always will be lesser than 0 at any point to the right of x1 in the interval ab. The point x equals to x1 corresponds to the maximum value of m of the function. It can be proved that the point x equals to x1, dy upon dx or f dash of x will be equal to 0. Similarly, consider the interval c and d on the curve. So in the interval CD, f of x decreases to the left of the point x equals to x2 and increases to the right of the point x equals to x2. Therefore, f of x attains its minimum value at point n, which corresponds to the point x equals to x2 in the interval CD. When the curve is decreasing, the slope of the curve is negative, and when the curve is increasing, it is positive. Since dy by dx gives the slope of the curve, again dy by dx or f dash x is lesser than 0 when x is lesser than x2, and dy by dx or f dash x will be greater than 0 when x is greater than x2. It can be proved that at the point x equals to x2, which corresponds to the minimum value of n of the function, dy by dx or f dash x will be equal to 0. If at a point x equals to x3 of the taken interval, fx is equal to 0, but f dash x does not change sign when x goes from the left of x3 to the right of x3, then x equals to x3 is neither the point of maximum nor the point of minimum. It is called the point of inflection. Note that the maximum value is m and the minimum value is n of the function. Fx only indicated intervals. They may not be the maximum or minimum values of the whole function. Now we need the following theorem to know about the function at x equals to c when f dash c is 0, that is when f dash x is either the maximum or the minimum or none at x equals to c. Let's see what is the theorem. The roots of the equations f dash x is equal to 0 for which f second derivation of fx is lesser than 0. It represents the points of maxima, and the roots of which where second differentiation of fx is greater than 0 represents the points of minima in the small interval around them. Now let's see the proof to this theorem. Let us consider f of x is maximum at x equals to c. As the curve passed through the point at x equals to c, f of x is passing from left to right. F dash c plus h is positive or negative according as h is negative or positive. F dash c plus h minus f dash c is greater than 0 according as h is lesser than 0 or h is greater than 0. So that implies that f dash c plus h minus f dash c divided by h will be lesser than 0 whether h is positive or negative. For a maximum f of c, second derivation of f of c will be lesser than 0. Similarly, it can be proved that for a minimum f of c, f double dash c will be greater than 0. If f dash c is equal to 0 and f double dash c is also equal to 0, then f of c is neither maximum nor minimum and c is called the point of inflection. However, if the third differentiation of c is equal to 0 and the fourth differentiation of c is not equal to 0, f of c is maximum or minimum according to as if the fourth differentiation of c is negative or positive. So in general, if n minus 1 differentiation of c is equal to 0 and if nth differentiation of c is not equal to 0, then if n is odd, then c is the point of inflection, and if n is even, then c is the point of maximum or minimum according as the nth differentiation of c is negative or positive. Now let's see what is the test for maximum and minimum. In the first step, what we do, first we find the first differentiation of x, that is f dash x. In the second step, we solve f dash x and we equate it to 0 and gets a value of x. Now let one of the values of x be x equals to c. In the third step, what we do is we find the second differentiation of x, that is f double dash x, and then we put the x equals to c to get f double dash c. Now if f double dash c is lesser than 0, so this implies x equals to c is the point of maxima. If f double dash c is greater than 0, then this implies x equals to c is a point of maxima. If f double dash c equals to 0, this implies that we have to further find the derivative and conclude accordingly. Now come to the example number 6. Find the maximum and minimum values of function f of x which is equal to x cubed minus 27x. Now let's see the solution. f of x is equal to x cube minus 27x. Therefore, first differentiation will be f dash x, that is equal to 3x square minus 27. So if f dash x is equal to 0, so that implies 3x square minus 27 will be equal to 0. So that implies x square minus 9 will be equal to 0. So that implies x square equal to 9. So that finally gives us x is equal to plus minus 3. Now we have two values for x, that is plus 3 and minus 3. Now we find the second differentiation of x. So second differentiation is equal to 6x. Now we'll put the value of positive 3 into the first differentiation and we'll find the value. So first differentiation of plus 3 will be 6 into 3, that is equal to 18, which is positive. In the second case, when you are putting minus 3, we find f dash minus 3 will be 6 into minus 3 and that is equal to minus 18, which is negative. Since the second differentiation of 3 is greater than 0, function of f of x is minimum at x is equal to 3, we'll say. And since that second differentiation of minus 3 is lesser than 0, so function of fx is maximum at x equals to minus 3. So therefore the maximum value will be equal to f of minus 3, that is equal to minus 3 the whole cube, minus 27 into minus 3, so that is equal to minus 27 plus 81, that is giving us 54. And we can find the minimum value as f of 3 equals to 3 raised to the power of 3 minus 27 into 3. So that is equal to 27 minus 81, which is giving us minus 54. Now let's come to the next example, example number 7. Find two positive numbers whose sum is 16 and the sum of whose cubes is minimum. Now let's see the solution to this. Sum of the numbers is equal to 16. Let one number be x. Therefore, another number will be 16 minus x. So the function will become as f of x is equal to x cube plus 16 minus x the whole cube. So f dash x will be to this function 3x square plus 3 into 16 minus x the whole square into minus 1. That is equal to 3x square minus 3 into 16 minus x the whole square. So we get it f dash x equals to 0. We know that f dash x is equal to 0, so we are equating 3x square minus 3 into 16 minus x the whole square is equal to 0. So that gives us 3x square is equal to 3 into 16 minus x the whole square. So x square will be 16 minus x the whole square and finally x will be 16 minus x. So 2x will be 16, that implies that x is going to be 8. Now we see that second differentiation of x is equal to 6 into x minus 3 into 2 into 16 minus x into minus 1, that is giving us 6x plus 6 into 16 minus x. Therefore, the second differentiation of 8, f double dash 8 will be equal to 6 into 8 plus 6 into 16 minus 8, that is equal to 48 plus 48, that is 96, which is positive. So f is minimum at x equal to 8. So the required numbers here will be x and 16 minus x, which is 8 and 8. Now come to the next example, that is example number 8. Show that the function f of x is equal to x cube minus 6x square plus 10 has the maximum value at x equals to 0 and minimum value at x equals to 4. We'll see the solution to this. We have f of x equals to x cube minus 6x square plus 10. So therefore f dash x is equal to 3x square minus 12x, that is equal to 3x into x minus 4. We know that f dash x is equal to 0, so this gives 3x into x minus 4 equals to 0. Therefore x is 0 or x minus 4 is equal to 0, that is x is equal to 4. So we have x is equal to 0 and x is equal to 4. For the point x is equal to 0, let us take x equals to minus 0.1 to the left of 0 and x equals to 0.1 to the right of 0. Then f dash minus 0.1 will be equal to 3 into minus 0.1 into minus 0.1 minus 4. That is equal to 3 into 0.1 into 4.1. That is equal to 1.23, which is greater than 0. And f dash 0.1 will be equal to 3 into 0.1 into 0.1 minus 4 is equal to 3 into 0.1 into minus 3.9, which is minus 1.17, which is lesser than 0. Since f dash x changes its sign from positive on the left of x equals to 0 to the negative on the right of x equals to 0, by the first derivative test, the point x equals to 0 is a point of local maxima. and the local maximum value will be f of 0, that is equal to 0 minus 6 into 0 plus 10, that will finally come as 10. Now consider x equals to 3.9 to the left of 4 and x equals to 4.1 to the right of 4. Then f dash 3.9 will be equal to 3 into 3.9 into 3.9 minus 4, so that will be lesser than 0. And we find that f dash 4.1 will be equal to 3 into 4.1 into 4.1 minus 4, which will be greater than 0. So as f dash x changes its sign from negative on the left of x equals to 4 to the positive on the right of x equal to 4, by the first derivative test, the point of x equal to 4 is a point of local minima, and the local minimum value will be f of 4, that is equal to 4 cube minus 6 into 4 square plus 10, so that is 64 minus 96 plus 10, so that is finally giving us minus 22. That brings us to the next example, example number 9. Examine the following functions for maxima and minima. So the functions are f of x is equal to x cube minus 6x square plus 12x minus 5, and the second function is f of x is equal to x cube minus 3x square plus 3x plus 7. Let's see the solution to the first one. F of x is equal to x cube minus 6x square plus 12x minus 5. So find the first differentiation to this, f dash x, which is equal to 3x square minus 12x plus 12. Also find the second differentiation here, f double dash x is equal to 6x minus 12. Now for the maximum and the minimum, we know that f dash x is equal to 0. So this gives us that 3x square minus 12x plus 12 equals to 0. So that implies 3 into x square minus 4x plus 4 equals to 0. That implies x square minus 4x plus 4 equals to 0. So this is giving us x minus 2 the whole square equals to 0. So that implies x minus 2 equals to 0, which is finally giving us x equals to 2. Now at x equals to 2, we are putting this value in the second differentiation. So f double dash 2 will be equal to 6 into 2 minus 12, which is equal to 0. Now since double differentiation is equal to 0, at x equals to 0, we will check the third differentiation at x equals to 2. There's a third differentiation of x will be equal to 6 and which will be greater than 0. So at the point x equals to 2. So hence we'll say that fx is neither the maximum nor the minimum at x equals to 2. Now let's come to the next function. F of x is equal to x cube minus 3x square plus 3x plus 7. Now find the first differentiation to this. We find it as f dash x equals to 3x square minus 6x plus 3, and the second differentiation to this will be 6x minus 6. Now for the maximum and minimum, we know that f dash x is equal to 0. So this gives us 3x square minus 6x plus 3 equals to 0. So that implies 3 into x square minus 2x plus 1 equals to 0. So that is equal to x square minus 2x plus 1 equals to 0. So this is giving us x equals to 1. Now at x equals to 1, we will put the value of 1 in the second differentiation and we'll find that f double dash 1 will be equal to 6 into 1 minus 6, so that is 0. Now since second differentiation of 1 is 0, we find the third differentiation at x equals to 1. So the third differentiation is equal to 6. Now since the third differentiation of 1 is greater than 0, this shows that function fx is neither maximum nor minimum at x equals to 1. So finally we have reached to the conclusion. So finally we have learned today derivative as a rate measure and related rates of change. We learned how to find the interval on which a given function is increasing or decreasing. Also we have understood how to find maximum and minimum values of a given function, related theorem, and the test for maximum and minimum. So finally, that brings us to the end of today's episode. We are ending here and we'll see you again discussing about our next topics on more wide variety of applications of differentiation to business and economics. Have a nice time. Thank you.